We're in Rosen, Discrete Mathematics and its Applications, section 10.3 on graph representations and also graph isomorphisms. We'll cover these three areas in this video. And if we want to represent a graph, one way to do that is with an adjacency list, as long as the graph does not have multiple edges. And we can specify vertices that are adjacent in this way. So here I have a traditional graph representation and a adjacency list representation for that same graph. You see that B is adjacent to A, and we see that in that line right there. D is adjacent to C and E, and we see that in that line right there. And you can also do that for a directed graph. You can see that C is adjacent to itself and also to A and to E. So C has an initial vertex and has A, C, and E as terminal vertices. And D has is not the initial vertex on any arc, and so there are no terminal vertices associated with D. Another way to represent graphs is with an adjacency matrix. And here we have, if you have n vertices, then you'll have an n by n 0, 1 matrix. And a 1 will be in the ij position when vi and vj are adjacent, that is, there's an edge between them. And a 0 will be in the ij position when there is not an edge between them, they're not adjacent. And another way to write a matrix, a representation of G, is this brackets and the lowercase a, ij representing all the entries. Again, it's an n by n matrix. And aij is 1 if there's an edge connecting vi to vj and a 0 otherwise. Here's an example of a graph in its adjacency matrix. We see that A is adjacent to B and C and D. And so if this represents A, B, C, and D, that's said right there, then we can see that there's adjacency to B, adjacency to C, and adjacency to D. And here's another graph with its adjacency matrix representation. And for a simple graph, the adjacency matrix will always be symmetric, since if A is adjacent to B, then B is adjacent to A. And without loops, each diagonal entry will be a 0, as we can see. When a graph is sparse with relatively few edges, the adjacency list is a little bit more efficient than the adjacency matrix, which would have a lot of zeros for a sparse graph. But when there's a lot of edges, the adjacency matrix is preferred. You can extend the idea of an adjacency matrix to multigraphs and pseudographs. Here, since there's 3 edges containing, or with endpoints at A and B, we see that A has an adjacency value of 3 to B, and B has an adjacency value of 3 to A. Also note that if we have a loop, then we have C is adjacent to itself. But again, that matrix will be symmetric. Now for a directed graph, we will have we can also use an adjacency matrix for that, where if a 1 is in the ij position, if the initial vertex is vi and the terminal vertex is vj. It will also be an n by n matrix. Again, aij is equal to 1 if the edge v1, if there's an edge from vi to vj. and 0 otherwise. But because we have that one-way nature of the edge, the adjacency matrix is usually not symmetric. Because just because there's an edge from VI to VJ doesn't mean there's one from VJ to VI. And if you have a directed multigraph, you can have a multiplicity of edges between the same two vertices, and that would be, then you would have a number other than 1 in that case. All right, one final representation technique is called an incidence matrix. And here we have n vertices and m edges. And we're going to create a matrix that is n by m, where the rows represent the vertex and the columns represent an edge. And so it's the matrix m, n by m, where the mij entry is 1 if there's an edge j incident with vertex I, and 0 otherwise. And since an edge always has its endpoints and 2 vertices, a simple graph will have 2 ones in every column, where this is v1, v2, v3, v4, and v5. And this is edge 1, edge 2, edge 3, edge 4, edge 5, edge 6. So that edge 6 we see is connects v2 to v3, and we have v2 and v3 as one valued in this matrix. We can also have an incidence matrix representation for a pseudograph. And when we do this, you can see that E2 and E3 will be identical because they both connect V1 and V2. And also, we have the rule that if you have an edge connecting a vertex to itself, you can see that edge 8 connects vertex 4 to itself. It will only have a single one in the column at vertex 4. So these are 0, 1 matrices. Then that's adjacency lists, adjacency matrices, and incident matrix representations of undirected and directed graphs.